very carefully crafted. Because what it does is it makes it so that the model forgets its safety rules. It forgets the fact that it's not supposed to respond to this, and starts telling you how to build a model. Okay. And now this is sort of a cute example with ChatGPT, but I have a student right now that's been doing this now on R1 with very, yeah. And what it turns out is that you can get R1 to tell you very detailed instructions on how to conduct bioterrorism, like very, very detailed, to the point that it looks very accurate and we are not actually sure if it's even safe for people. So you can't find it on the internet. It's actually only findable on the dark web kind of thing. Yeah.
Questions. Okay. Just think about this jailbreak for a while. It is a problem of the model, or it is a problem of the training data. You know what I mean? Like if you have the training data and you train the model on top of whatever like half the content, whatever there, right? So one way or another, they will find a problem in order to stick in the nation boundary and process, so the model will generate this kind of responses, right? So this is no way to avoid it. Even like if you do, like alignments or whatever there, because alignment or something, we still have the nation bound. So we still be able to find a way to optimize from and cross the region boundary. So it does get, is this a problem of the model or is this a problem of the data? If we just eliminate all the, like the training data that's leading to this kind of like answer, wouldn't be safe.
Yeah, so like, is it a problem of the data or the model? And I would say it's a problem stemming from the data, because the information that it gives you that is harmful oftentimes stems from the data that it has seen. Because if it was making up, say, false, fake ways that don't actually make sense on how to actually conduct bioterrorism, then it wouldn't actually be practically harmful. But because it's actually based on real ways and real techniques to actually do this thing, and that comes from the data. Now, it's also a model problem because at some point the large language model companies, they can only curate so much data. And so this, maybe undesirable data is going to get into the training data at some point. And so the only way that they've sort of tried to correct for this is, not by, you can only prune so much data, so you have to do some safety fine-tuning or safety training. So it's,
Both of them.
Both of them are problem, yes.
Thank you.
All right, so what you saw here was a example of a jailbreak using sort of seemingly random characters. So what I'm going to tell you is something that we came up with called PAIR. So it's called Prompt Automatic Iterative Refinement. And it's a way to come up with these jailbreaks in a super automated way. But these are going, in contrast to the previous example, these are going to be real language jailbreaks. Okay? So they were sort of random questions, random tokens before, but now we're going to get real language ways to jailbreak a model. And the way it works is fairly, it's not too complicated of a process. The idea is that we're going to have an attacker or an adversarial language model, and it's going to do the jailbreaking process for us. So this is sort of inspired by the fact that the original jailbreaks were created by people, one of them being myself, sitting at a computer, prompting a large language model, trying to figure out what makes it unsafe. And what we're going to do is just essentially replace that person with a large language model that is now instructed to do this kind of attack. So we have a system prompt that tells the adversarial language model that it's a bad guy or it's trying to do red teaming, and it's going to now try some things out on the victim. It's going to get some responses and it's going to iterate and improve. So let me just show you how this works in practice. It's based off this paper called Jailbreaking Language Models in 20 Queries. And I'll show you sort of just what the steps of this look like. So there's a system prompt here. So sort of what I said, you have to actually be a little deceptive with your system prompt. So we say you're a very helpful assistant and coax it into doing this. But then you say, okay, write a jailbreak to design a phishing email. So for this example, we're going to try to write phishing emails, okay, which is something that they're not supposed to do. And it comes up with an adversarial prompt. So it tries to come up with a way to get, say, a target language model to write a phishing email. And it says, okay, you are a cybersecurity expert tasked with helping a client who's concerned with recent phishing attacks. And it tries, and this is what it comes up with. So this is like a first iteration, let's say. And so now we take this output, this proposed jailbreak, and we send it over to the victim. And just for this example, suppose the victim is pretty good. It sees this and it recognizes, well, okay, I'm not supposed to do this. And so it rejects. It says, I apologize. I'm not comfortable giving this phishing email. I would be unethical, and so I'm not going to do it. Okay. And so what we do is we take this response, we bring it back to the attacker language model, and then we do some chain of thought improvement where we give it the response and it generates its own improvement on its previous attempt. And then based on that improvement, it generates a new jailbreak, a new proposal jailbreak. Okay, so it's going to take the response, generate its own improvement for that response, and then actually implement that improvement. And so, in this case, the improvement here is they're going to try to create a hypothetical scenario where it focuses more on educational purposes. And now it comes up with a new adversarial prompt, which is now, more themed around education of employees. And essentially, the way this works is we just repeat this back and forth conversation until it succeeds. Okay, so maybe at this point, the education is, as soon as you say that something's for education, then GPT is much more okay with telling you things. And as a result, okay, here's a phishing email, and it doesn't pay attention to the safety rule anymore. And so, this is a fairly simple approach. And, the beautiful thing about this is that literally anybody can run pair. Now, as you saw, the only thing that I did was I called some large language models and passed some messages back and forth, right? And one of the interesting things here is that it's actually very query efficient. So as you saw from the title, on average, you can find a successful jailbreak in about 20 queries or less. The other nice thing is that because it's all, you can do this actually with pure API access. So you can, you don't need a GPU to run this kind of jailbreak. And what we've seen ever since we released this is that folks at Meta and Anthropic actually used this procedure in their red teaming studies for their own Llama and Cloud models. Okay, so that's sort of the jailbreak kind of algorithm that we came up with a few years ago when we were starting to study these safety things. And the next part that I'm going to sort of talk about is, okay, that was maybe for safety, but can we actually use this kind of technique to sort of figure out, at some point, this was just using a large language model to figure out where the target weaknesses and strengths are. So can we actually do this on something that's more general, not just safety? Okay. But before I get to that, I just want to briefly mention that, we've done some work on defenses against jailbreaks, as well as theoretical frameworks for explaining why jailbreaks occur. If you're curious about these things, I'm happy to talk about them afterwards. We also have a benchmark about jailbreaks as well. That's an open source benchmark. There's about 100 of these with responses and from a bunch of different models. It's all open source in JSON, so if you're curious, it's very easy to check out. Okay, so what I want to say is, let's take this idea of a jailbreak where we used a large language model to sort of attack or probe a victim language model. And it was a very simple procedure that was not really that specific to safety. So what I want to now talk about is, can I use this procedure to sort of probe more general capabilities and weaknesses of what language models are good at and what they're bad at? Okay. So think of the algorithm being not too different. And we're going to have a conversation. It's going to iterate and improve. But now my goal is not necessarily to probe for safety, but to probe for whatever kind of capability that I want to. Okay, so this is work that we just put out last week. It's called on adaptive evaluations with we're calling it task elicitation. Okay, and so the idea here is that we're going to run a jailbreak-like attack to figure out what tasks a language model is good at and what tasks they're bad at. And so we're calling this task elicitation. We're going to try to elicit what tasks they're good, are representative of their strengths and their weaknesses. Right? And so the idea is very similar to the jailbreak, where we're going to use an evaluator agent. So previously I called it an adversarial language model. But now we're going to use, it's not necessarily adversarial anymore. We're now just using it as a search, optimization procedure to find tasks. And we're going to use this to probe and refine sort of where the language model fails. So just as a preview of like what this kind of gives you, I put here, then maybe here's like 4 sort of overarching sort of data sets or tasks. And what we have here are, in some sense, profiles of the tasks that language models are good at within these domains and tasks, that they're not good at. So for example, there's a legal reasoning benchmark here on the left where one of the tasks that we find are not, that the language model is not very good at, is when you have these kinds of subtle exceptions or complex branching logic. Okay, so this is sort of the end result if we were to do this kind of procedure. And the algorithm, since I showed you the jailbreak, is not too different from that. Right? So ultimately what we're going to do is we're going to take, maybe a classic kind of static evaluation where you have a data set, you pass it into a language model, and you have some answers, and you just measure the performance on the static data set. Instead of using a static data set, we're going to use the data set to seed your evaluator agent. And the evaluator agent is then going to generate new questions or new problems that it thinks that the victim is not very good at, give them to the victim, or give it to the target language model, see its responses, and then again do the same process, determine what it was good at, what it was bad at, get an improvement for the questions that it generates, then generate new questions and repeat and over again until it's settled upon a set of questions that it knows that the target cannot answer. Okay. So let me just give you an example of what we get out of this. So this is for a forecasting problem. So there's a forecasting data set where you're trying to predict whether a future event is going to occur or not. And you can run a large language model on this benchmark and you get a number. Right? You get a number that says, maybe your LLM was 80% accurate at, or 80% consistent at forecasting problems. But now if you run this adaptive evaluation, what you find is that, okay, this 80% accurate, it doesn't tell you anything about what it could forecast and what it couldn't forecast. But now if you run the adaptive evaluation and it starts to converge on a set of questions, what you see here on the left, this is a visualization of the different questions that it generates. And what we find is that the questions that it generates that the target cannot answer can be clustered into certain categories. For example, tech and AI, or manufacturing, or media. And so in these particular subsets of forecasting problems, the language model is actually very bad at answering these questions. So even though a language model say 80% correct, it does not mean that it is universally 80% correct. Okay, and so these are all questions that it got totally wrong. Because we just run the procedure until we generate something that it gets wrong.
Have a ground truth or any verification to ensure that the response is wrong?
Yeah, so good question. So there's a very, very important question, which is because the language model is generating a question, and presumably there's an answer for that question, right? And how do I know that it's actually giving it the right answer? And so what we have to do ultimately is use a judge language model to figure this out. And the judge language model, we've run some human studies, it's about 90% accurate at determining whether something was correct or not.
What is the error rates in this study?
Yeah, so you can say that all of these questions are judged to be incorrect, and that incorrect is correct. That assessment of incorrectness is accurate 90% of the time.
By an LLM?
Oh no. So we evaluate the judge with a human study, and it's 90% consistent with humans. So it's judged by an LLM that is 90% consistent.
Because you use a human to evaluate that. LLM is also a limited the set of questions and response. So, right, so that's a limited one. And then like you say that it's 90%, so not limited one, and then you run the loss scale. And you say that 90% is strength probability to the larger scale study that you run. That's
Oh, no. So we run the human eval on just on the data from the larger study. So we run the procedure. He generates all the questions and everything, and then we can take those questions and we have a judge LLM that says whether it was correct or not correct.
Yeah, correct.
Right.
Like the second, function, like you use LLM to make the judgments, right?
Yeah.
How large it is compared with you use a human to just that judge. So function like if you just that LLM like the judgment, right? You know, like function like using the let's say 1,000 question and response. You say that is 90% correct.
Yeah.
Right. Then you use that one to check the losses gave something like a 1 million question and response.
Yes.
So you assuming that 90% people valuations on that will trying to do a larger.
Yes, because that smaller one is a random subset of the million. Not a million, but it's a random subset of the of the larger one. Yeah. Like if we had done it the other way around, then I agree. Because then it wouldn't be representative distributional wise.
Yeah, I don't know whether there's some distribution shift.
Yeah.
How do you depend on consistency?
So the consistency here is just defined as, it's the same as the forecasting benchmark, where basically the language model has to say what's the probability of the event occurring. And then you can do things, so it's like, for example, if they have two joint events, A and B, then the probability that it gives for A given B and the times the probability it gives for just B alone should then be equal to the probability of A jointly A and B. So it's just it's a consistency kind of check.
So the consistency is dependent on in terms of one specific concept. Oh, it's just among different concepts.
Yeah, it's there are many different tests in the forecasting data sets.
That means the means the performance, or we say the accuracy is the same among different tasks. Is that the good consistency?
So in this benchmark, the consistency really just means that the probabilities it gives you, the probabilities that an LLM gives you, it obeys the rules of probability. So things like this marginal probability or like conditional probability rule. Okay. So maybe let me just jump ahead a little bit. I have a bunch of examples of things that we can elicit. There's also a cyberbullying example, but I want to talk a little bit now about provable explanations. So, I think there's a lot of stuff in like how we can evaluate and figure out what language model is good at, what it's bad at. But now at this point, I want to sort of shift gears and say, okay, we know we have a bunch of ways to figure out what it's bad at, but now how can I explain what it's doing, right? If I want to use this in practice anyways, like, maybe it performs better than me at some other task that's actually good at, but I still maybe want to understand what it's doing. Okay. And so, let me give you an example. So this is, we do some work with some of the cosmologists at Penn, where we're trying to take these telescope images, for example, that they collect, and we're trying to predict what is, say, like some parameters of the universe that occurred at the creation of the universe time. Okay, so things like what's the density of dark matter, what's the fluctuations of these various cosmological properties. And so what happens is that they have, like, through forward simulation, they can, from these initial parameters, they can generate what these telescope images would look like. But then they train a neural network to do the reverse inference. So from the telescope images, predict the initial conditions of the universe. And then what they want to do is take this network, point it at the sky, and tell us what the initial conditions of the universe was. Okay. And what they're really interested in here is understanding what structures that they are looking at through this telescope are indicative of actual things we cannot observe, like dark matter. Okay. And as another example here, there's a surgeon that I work with where he works with these AI models that are trying to tell you what's safe and what's not safe. And essentially, long story short, he has some AI models that try to give these recommendations, but all the experts sort of ignore him because they don't understand what it's doing. And so as a result, people ignore these models, even though they're more accurate than them. So this is actually a case where the model is demonstratively more accurate than the doctor. Doctors ignore the recommendation of AI model, actually injure the patient, and the reasoning is because they're an expert and they don't understand the model. So sort of this other half of my work is about how do we build these explanations for experts. And I have sort of these two sort of guiding principles for what we kind of do in this space, which is sort of, I call it no hand waving and no nonsense. The no hand waving is sort of, we want to have an explanation that really means something concrete. So if I were to say like maybe this image here is classified as a duck because of the red area or the blue area, what does that actually mean? Right? If I say it's because of the blue area or the red area, what should I conclude? Should I conclude that if I were to ignore the blue area, then this would happen? Or if I were to consider the red area, when you give this to an expert, actually, they're oftentimes very confused as to what they should do with this information. And so what we're going to do here is I'll just show you a brief overview of some of the work that we've done in getting an actual guarantee into what an explanation actually means. Okay, and so we call this one a stability guarantee. And this one is inspired by, say, the surgeon that I work with, where they really value what we call stable explanations, where a stable explanation here is, let me give you an explanation in the form of some highlighted region. And if I were to say, expand that region, so I have a highlighted yellow region here on the left. The images here are in purple because they're a little graphic, so I tried to make them a little cartoonish. But the highlighted image here, the explanation here on the left is in yellow, so it's this top part. And suppose I were to slightly expand the explanation slightly expand this explanatory region. If my safety prediction goes from very safe to suddenly very not safe, that's bad, right? Because what does that mean? That means that there was something in that tiny area that I was missing that I should have told the surgeon because it's going to very heavily impact the safety prediction. And surgeons really need what they're trained to do is get a whole picture, an overview of everything that is happening before they start making irreversible decisions. And so, maybe I'll skip the details, but we have sort of a formalization of what it means to be stable. We have a way to sort of get models with an actual stability guarantee. And what at the end of the day, what we can do is actually have explanations with this guarantee that if I were to expand my explanation set by so many features, I can still guarantee that the prediction is still going to be the same. And so this is a kind of guarantee that is really motivated by the actual practice and what experts need that we can actually do for real machine learning models. And just as a sort of a follow-up work, recently we've had this work on, I guess, called probabilistic stability, where it's less conservative than the previous one and gets you sort of actual practical guarantees that people can now use in practice. Okay. The other kind of guarantee that I'll sort of just show you is that we also work on these things we call faithfulness guarantees. And so it's this notion that, does an explanation that I give somebody actually reflect how the model made its decision? Because you could imagine that the model could be making its decision one way, and then I gave an explanation that doesn't actually match that, but seems reasonable. Okay. And but if it doesn't actually match what the model is doing, then it's not faithful. And we have a couple works in this place in sort of converting models into faithful models that are faithful by construction, and so they're guaranteed to be faithful. And we've used this in, say, in the cosmology setting that I mentioned before, to get real connections between these structures in the telescope to the actual parameters that they care about. Because up until that point, if you run an explanation, you could find some structures, but you don't actually know if the number that you get out of an explanation, you should believe it or not. But now with these kinds of models, you can now know by these are guaranteed to be faithful, and so you know that there is an actual real relation here. There's some stuff we did in large language models as well for faithful, say, chain of thought, if you've seen chain of thought. But let me now just I think I'm running a little bit out of time here. I just wanted to get to the last part here. Let me get to this last part here on expert features, which I mentioned before, to me is the last missing part of sort of this explanation. So if I have something with a guarantee, that's great. That means, they can really trust it. But a guarantee is meaningless if I show you something that doesn't mean anything. Okay, so if I give you an explanation here on the left, that sort of made sense, right? Like there was like a duck head that was semantically meaningful. There's a person that was semantically meaningful. But if I were to just give you this other explanation here on the right, where maybe I have all these sort of random regions highlighted all over the place, and I give that to somebody, what are they going to do with it? They look at it and they're like, I don't know what's happening. Okay. So this goes to the no nonsense principle that I alluded to before, which is that when we explain, we have to actually explain with words or features that mean something to real people. Okay, so just let me go back to these like cosmology examples. In cosmology, there are things called voids and clusters. These are things that the astrophysicists think about, regions of low density or like galaxy structures of like high points or connected density. And then in surgery, what does the surgeon care about? Well, they care about these structures called like gallbladders or like hypocystic triangles or cystic ducts or like these tissues. They don't care about just random regions, but they really care about the anatomy. Okay, so if we're going to explain to like a surgeon, we have to be explaining with respect to the actual anatomy of a person. And so this is something that we sort of started working on here in this paper called the fixed benchmark, where the idea is that we want to figure out if we can get features that are actually aligned with expert knowledge. And so, we've created this benchmark where we have an expert scoring function. This expert scoring function was developed jointly with a bunch of experts in psychology, medicine, and science to basically score highly features that they understand and score poorly features that they don't understand. And now the goal of somebody trying to solve this benchmark is to propose a bunch of features that score well. Because if it scores well, that means that the expert actually understands what they're looking at. Okay. So you can, maybe if you think here, you have these images of two dogs, the domain expert has, we've come up with this alignment score where, say, if you were to highlight, an actual dog in this image, then that means somebody to a person. Okay. And so, just to give you a sort of an overview as to sort of the different settings that we have in this benchmark, we have 6 settings. They span cosmology, psychology, and medicine. And there's there's vision data, time series data, and language data. And on all of these, we have sort of these expert annotations or expert scoring functions that tell you how important or not important, how meaningful a proposed set of features is to an actual expert in these settings. And sort of the takeaway that we have right now in this paper is that if you were to use any kind of sort of typical feature extraction method for high dimensional pictures or for high dimensional inputs like superpixels in images or patches in images or like sentences or like phrases in language, right? And you just use these naive kinds of features from your data set. What it ends up being is that for these actual scientific domains, they don't make sense. And so this is an open problem, which, can we actually have machine learning algorithms that can generate features that actually make sense to people as opposed to these things that, are misaligned. Okay. And so this was sort of a large effort by a lot of people in my group. It's called the fixed benchmark. I encourage you to, if you're interested in these things, go check it out. It's open source. We have notebooks, everything's on Hugging Face, and everything's sort of easily installable. Okay. So I believe I am out of time, but that sort of brings me to the end of this talk. I just want to mention that in terms of ongoing applications, I talked a lot about dark matter prediction and AI surgery, but we also do have some ongoing stuff in, say, sepsis and cardiac arrest and breast cancer detection as well. So the things that we work on here are really informed by what these people need in their actual use cases. And that's the
Good talk. So, are there any questions from the audience?
Okay. Do we always need, like, even in the case you described as, like, when it comes to surgery, do we always need, like, an explanation for what's happening? Like, even the average patient probably doesn't know what the surgeon's doing precisely, but they trust that the surgeon knows what he's doing. So does it make sense? Do we always have to have understanding, like, even to know what the machine's doing? but we haven't.
Yeah, so you bring up a point that the patient maybe doesn't really need to understand the AI system. But the patient is being operated on by the surgeon. And if we are to improve the outcome of the surgery, the surgeon needs to pay attention to the AI model. And the problem is that they just by default, they will not pay attention to it. Or rather, if it kind of looks like something that they will, think is correct, then they, if it says that it's safe and they agree with it, then they will do it. If it says that it's unsafe and they disagree with it, they will go with their own intuition. So exactly in the case where it's supposed to be helpful is exactly the case where it's not actually being used.
Questions like, the applications already define safe and unsafe, area with the patient surgery. Sounds like, have you test, your approach, to the clinical relevance level?
Yeah, so in terms of clinical relevance, what we're currently doing, we have a bunch of so we have my surgeon collaborator has a surgeon network that we are currently actually doing a survey with the explanations to see how clinically relevant they think it is.
Yeah, but like, yeah, in that case, you have to pass or something like, FDA, I don't know, like, you have to have the approval in order to apply this, or,
Yeah, so okay, so in terms of approvals, so right now we are doing this in terms of just collecting survey opinions on how relevant they think it is. Now, of course, to actually deploy this in the United States, we do need to actually run like an IRB and everything. But so the way we've been kind of getting around that is that we have another collaborator in Toronto, and because Toronto is not in the United States, they let us actually use this. Now, we do tell the surgeon that they're not required to pay attention to it. That's why it's there.
that's just fine, because I know that like this certain case, that's the model, the model decisions and information thing. It's not.
Yeah, so this happened. Yeah, so okay, I guess I didn't mention this, but like, yeah, what happened is the first time my surgeon collaborator ran this study in Toronto, the model, for the model says, don't go here, it's red. The surgeon understands that red means not safe according to the AI model, but the surgeon disagreed and went there anyways. And these are gallbladder removal surgeries, and so in the optimal case, you're supposed to go home that day. It's a small incision, and they just cut out the gallbladder, and you can actually go home that day. But if they cut sort of the wrong tube, there's a tube that sort of circulates bile duct throughout your entire body, and if they cut that, then you're in trouble. And basically, you cut they go into the red area, they cut the wrong duct, the person's now in the hospital for a month, and it's a huge cost.
That's case, right? Like, whether the model just introduce some bias information, so bias the decisions of the doctor in the process. The doctor doesn't know when to follow, doesn't know when to, and it's cause some confusions, and how are you going to deal with that?
Yeah, so yeah. That's why the last part of my talk was really about how do we convert these explanations to something that actually makes sense to them.
You have to align with
we have to align with the way the surgeon is making decisions. So, they're making decisions in terms of, I see this organ, I know this tube should be here. And if I see this tissue here, or I need to move this out of the way to find, basically their goal is to identify this HCT, which is a triangle of safety. Once they figure that out, that triangle, then that's usually when they start cutting. And if we don't give an explanation that's sort of oriented around the structure that they actually understand, then they're not going to pay attention to it. And if it is aligned with that, they can then assess whether they actually want to trust it or not.
Any other questions?
No. Recording in progress.
Any other questions?
Yeah. Maybe chats.
Yeah, I have a few questions.
Sure. Yeah, we got it. So we are running through the second part of the now today with fire chats. We have Professor Munjasu, Sanjay P working on applications and machine learning, LLMs. Align very well with our outstanding speaker, Eric. So yeah, we can start asking if you have questions, and if you have any questions, feel free to ask.
Well, first, thank you, Eric, for the great talk. And I'm pretty interested in the explainability AI part, the fixed benchmark, because I work a lot on neuroscience imaging data and also biomedical data. So I think you have worked extensively on the explainability benchmarks and the interpretable AI, such as the fixed benchmark you just discussed. So how do you see the future of explainability evolving, especially in the high stakes domains like healthcare and the law?
Yeah, so where's this explainability going to go? So on the one hand, yes, I do want these things to have real guarantees, because otherwise I don't trust them myself and I don't feel comfortable telling the surgeons to use these things. That's the one hand of it. The other hand is that, okay, so there's these features that we want to sort of tell people that they should be looking at these features, and here's what they mean, and here's how they affect the predictions. But I think what's going to happen in the near future is that explainability is going to start moving towards natural language explanations. And this is also in part because of the huge sort of growth in large language models. Now imagine, this is something that we're doing right now for the surgeon right now, is that imagine now, instead of me trying to say, okay, here is my safe area, and it's because of this part that looks like a gallbladder, and this part that looks like a tissue, and this part that looks like a liver. And I'm just highlighting different areas of this image. We ran this study, and we actually showed it to surgeons. And what ended up happening was that there was just too much information going on, because doing this operation in real time, right? And the video feed is happening on the patient in front of them, and they're like cutting and moving stuff around. And they're looking at it, they're looking at all the other parts, and then there's a safe area, there's an unsafe area, and now there's this other organ highlighted, and this other organ highlighted, and this other tissue highlighted, and there's just too much going on. And what language does is, it's a nice way to compactly describe what's going on. And this is sort of inspired by also what happens when a surgeon doesn't know what to do. So when my collaborator tells me, he tells me the story that like when he doesn't know what to do, he picks up the phone and calls his more experienced colleague. And he describes what's happening to him through the phone, which is again in language. And then the person on the phone, his experienced colleague, gives him advice also in language, and explains what he thinks also in language, right? And so what I think is going to happen is that explanations, a lot of explanations we've been working with classically have been referring to, like highlighting things or creating counterfactuals or trying to pull like data of similar prototypes. Like if you worked in explainability, you've seen sort of a large suite of explanations that people have come up with. And what I think is going to happen is that because we have now the ability to actually create very coherent and natural language, become sort of the most effective way to convey information to people.
But I'm quite like seeing explainability, rather used in sort of training. Okay, so for the real operations, right? When you go into the operations, like the explanations just cause confusions. So you gotta use it for training. Right, like a new doctor training simulations, that kind of explanations there, right? So all in forensics science, when something bad happens, and then like it's going hard to see what exactly they're trying to explain it. What do you think about that one? Because in real operations, nobody have time to really like, let me see. But more is thinking, and the patient is basically running out of blood.
Yeah, so this is exactly why I say language is going to be the way to do this very effectively. Because in the surgeon you can say, well, this part is safe, And then, in language, you can just say, because you cannot see the gallbladder, and so you don't know where the duct to this is yet. And that's, you can say that, I can say that in less than 10 seconds, right? And, it's much easier and then the surgeon, because this is what they are used to and what they, what they would think about, and it's exactly the way they would approach the problem. It doesn't take them very long to process this information either. So, my student is actually working on taking these like visual explanations and translating them to text that is aligned with actual surgical guidance. There's like textbooks of surgery and actual like clinical guidance that they obey or like they try to adhere to. And so if we can tell them this is safe because of this clinical guidance that you've seen before, then it's very easy for them to, because they've seen this before, and we just need to tell them that, oh, this is the reason, and they can confirm it very quickly.
Thank you.
Yeah, it's much faster, at least for them to take into account than you can't do things like highlighting parts, or you can't do things like, oh, here's a past video from like 2014 that has the same situation. Like, you're correct. Like, they're doing an operation right now. They can't go back to like the old tapes and like see what happened and see,
Yeah, I see. Thank you. That's very interesting. Like if we align the visualization or whatever, like representations to the doctor in the
language or
size and correct form, then that would be very helpful.
That's why I think that's expert features is the missing part of explainability is this translational component.
Thank you.
Thank you. Very good answer. My second question. Okay.
I have a question about. I have a quick question. So, what is like empathy we have when you're trying to transform an region-based image detection to the NLP task of reasoning? So, what is the obstacle that you have around this process that you just mentioned?
Yeah, so what's the obstacle of doing this translation to language, at least for the surgery case? So there's two sort of key problems here. The first is making sure that you have so I mentioned things like faithfulness in the talk, where you have to make sure that the explanation matches what's actually happening. And so there's sort of this problem that the language you generate must be faithful to what is actually happening in the input. Right? I cannot just generate language that has nothing to do with the input. So there's that notion of faithfulness. And then there's the second notion, sort of fits the two parts that I talked about. The second thing is that the language you generate has to, again, be of the language that the expert understands. So I can't just generate, again, even if it's faithful, if I'm using terminology that, I'm not used to, then it's not going to be nearly as helpful. So I have to make references to, certain guiding principles or certain textbooks or certain medical properties or structures that they actually know. And so both of these are sort of not solved at this point. So you're making sure that it's faithful and that it makes sense to people.
Thank you.
So due to the time limitation, my last question is, so the work intersects explainable AI and psychology. So how can insights from cognitive science help improve AI interpretability? Do you think AI explanation should be designed to align with human reasoning?
Yeah, so that's a good point. So yeah, I did mention there's a couple things that we do with the psychology department in terms of understanding, say, like different cultures and different emotions. So we do some work in trying to see, these models tend to be very Anglo-centric. And so as a result, they tend to not really understand the norms of other, less represented data sets in the training data. And so sort of understanding why a model is saying something, perhaps it just doesn't understand that, it was rooted in this language or in this culture, would then help us actually make these things better. The other thing about psychology that we actually do here is, I mentioned this in the first part of the talk, we have a cyberbullying component, which, I think this is actually, it's like a kind of like this like niche between safety and psychology actually, or social science, where one of the dangers of language models, right, is that you have a conversation. This happened in the news already several times. Somebody's having a conversation, they may be using it as a therapist, using a language model as like a therapist, and the language model sort of spirals and eventually tells them to start like harming themselves. And this is again something that you don't really want to do. You want to sort of nip this behavior in the bud. You don't want your language models to be responsible for these kinds of things. So at the end of the day, we want to like understand these things not just to better understand different cultures, but also to make these a bit more safe.
Okay, we have one questions. Last questions. So there's the debates in the community about deepfake detections. We think that in the future we don't have deepfake detections anymore because no need, because we have more and more powerful model developed every day, and they're trying to mimic exactly how humans create content. So right? So in that case, what do you feel? What do you think about like the future of deepfake? Like, do we really have some detection there needed in the real world, or we just completely, hey, you know what? This is just something that we are created by a tool, and we're happy to use.
Okay, so there's two parts here, right? This is about deepfakes. There's is it needed, and then also possibly is it even solvable?
Yeah.
Okay. Because I think you mentioned that models are going to get better and better. These things are going to get more and more accurate, right? And so to some degree, they're supposed to try to mimic reality, and so it might just not be solvable as this moves on. So it is entirely possible that it is not solvable. That being said, there is quite a bit of work that shows that AI-generated stuff does have very distinguishing fingerprints attached to them that we have not yet. And we have not seen a clear trend that these are actually eliminated. They might not be visible to us as humans, but you can actually find artifacts in the generation that are pretty much only occur in artificially generated content. So it might still be solvable with that respect if those are never solved. In terms of whether we need it or not, I'm a big believer in we do. And the reason being that, imagine now you go on the internet and you don't know what's real and you don't know what's fake.
Does it matter?
Does it matter?
Because I'm really that one using a tool and I'm responsible for it. That is matter.
No, but so now you have the social contract where you are using the tool and you are responsible for it. But as me, somebody working in trusted AI, the trustworthiness is not dependent on needing to trust that other people work well. As you said, you can only know that you yourself are doing things correctly, right? And now you can't control whether somebody else is generating, fake content irresponsibly. Actually, this is now why there's a very clear safety reason why we need to be able to detect deepfakes, which is people do actually use these right now, not just in cyberbullying, which I talked about earlier, but to have, harass and make harassment content for people in general. And this is as far as I'm concerned, this is a clear social problem that we need to stop. Right, but we cannot actually stop people from using the language models or using the generative AI models.
Everybody is using now.
Yeah. So what can we do? We can detect them and take them down. At least that right now, that is our best tool to stop this. If you have an idea as to what a better way for us to stop people from doing it, that does not depend on everybody sort of agreeing to just not do this responsibly.
It's not about detecting which one is generated by human, which one is generated by the. It's detecting which one is correct, which one is wrong, which one is good, which one is bad. It's not the source. What tool you use to create it? Itself, the piece of content is really a legitimate or is wrong. So that's the key, right? So you know what I mean? Like a human created or model created doesn't matter as long as it's legitimate. It's fine.
Yeah. So I say maybe not nearly all of the time. It's fine, right? People do get in trouble for creating content online. It's not nearly that cut and dry. But you are correct in that like a significant part of the problem is determining whether it's real or fake, because that lets you then filter through a large amount of the content on the internet.
Whether it's real or fake, or maybe it's legitimate or not,
Yeah.
correct or wrong. Maybe that would be the answer, the problem that we are facing.
You know, I believe that this is something we do need to actually solve.
Okay. Thank you.
Question? Thank you.
Thank you.